Ready to go. Okay, let us go ahead and get ourselves started. Talk about what we're going to be talking about today. Because today we're actually going to be doing a little bit of design work. We're actually going to go into Revit and be messing around in there, kind of working with walls and windows and kind of some of the surfaces kind of hanging around in there. Really actually doing design work and then thinking about how all that gets reflected back in the energy analysis packages. So, the science is still behind everything we're doing here. My calendar is still behind everything we're doing here, but you don't want to see all that. But what we're going to be doing is kind of starting the whole process of really trying to take a building and design it towards a program and be thinking about how all these different issues kind of play in and how we reflect them in the design of the building, how we can actually use the tools to help us inform our design. So as we're going through, we're making sure that we're designing and according to all the right principles. So at a high level, what we're going to be really thinking about today is a lot of the aspects about how the building is affected by the sun, kind of continuing with that. And then especially be looking at the whole issue of really how light is kind of infiltrating the building and what we can do about that. So the sun as a source of energy kind of beating down on the outside of the building, which is kind of giving radiant heat to the building and the building surfaces absorbing and kind of re-radiating through the sun. That's one piece of the equation in terms of what's going on. One of the other pieces of it is about daylight and really what the impact of the sun is relative to that and how it impacts all the different other energy loads. Okay. Along the way, we want to talk about one other kind of property of materials. That's the thermal mass of materials, which is a very important one. As we think about materials and how they absorb heat and then re-radiate the heat, different materials have a different quality of this notion we call thermal mass. And kind of very thick, heavy materials like concrete. Okay, they're very thick, they're very heavy, they're kind of very slow to absorb energy, but at the same time, once they've absorbed that energy, they're very slow to re-radiate that energy back into the system. So they're actually quite good. You can almost think of them like little thermal batteries, where once they absorb that energy, they kind of buffer the effect of anything happening from the outside world, but at the same time, they also kind of maintain a relatively constant temperature and re-radiate at a relatively slow level. So they're really good, just kind of dampers. They kind of minimize and store kind of all at the same time. So think about how materials get reflected or accounted for that way. And think about specifically, relative to windows and different sort of openings within our building, really how we handle this with shading and reflection and ultimately affects daylighting. So let us think, let's just kind of go on ahead and open up Revit. We'll sort of start with some of these concepts and we'll start to think about how some of them are interrelated. Okay, so what I'm going to do is actually go into Autodesk Revit. So if you can, please go ahead and, I'll say no to that. I got all sorts of things going on my machine over here. Let me go ahead and make that full screen. Hopefully that's working out okay. Let us then go through and open up Revit. And if you can do this on your machine too, I'd love to have you play along today, because really what we're going to do is less lecturing, kind of more playing around with different systems and like you sort of see how you actually play with these things, because you're going to be starting to do the same sort of thing. In terms of the overall direction of the course, what you should know is that relative to project work and things you'll be working on, starting on Tuesday, we're going to introduce a project that you're actually going to follow through and kind of keep on building on throughout the entire quarter. We kind of thought of a lot of ways about how we could go through and kind of build the assignments to go ahead and match the different material. And after working with the teaching team, we sort of decided one of the best ways would actually be to give you somewhat of an architectural program to kind of deliver on, let you do some design work towards that program, but then really think about how each of these different principles apply to that and take a building really from the conceptual stage all the way through the very fully developed stage, where we'll start by kind of thinking about the building envelope and qualities that you'll design around that. But then, design the structure and all the structural elements and the analysis to kind of size them and go through and design the different building systems really for that specific building in the climate that you choose. So it's really the idea of kind of an integrated thing that will keep on building so that by the end of the quarter, you'll have a very well-developed building that hopefully will keep evolving and changing as we learn more, you gain sort of maturity with it, but at the same time, hopefully you'll care about it, as opposed to all these assignments where I give you kind of a box and you design the box and you throw it away in 2 weeks and you don't care about it anymore. So we want to give you something that's hopefully a little more fun to work with. And we're going to introduce that to you on Tuesday. For today, let's go ahead and just kind of start building something that'll give you an idea of really what you're going to be doing on your own. And I'm going to start with just new and go to the architectural template. Say OK to that. And we'll go ahead and get ourselves started. So what we are going to do is we should ultimately choose a location for our building. And for this building, I'll go with most anything. How about if this building, what do we want to do with this one? How about for today, we'll just put it kind of as though it's here on the campus, something like that. That's actually relatively easy to do. So what we'll do is to start with locating our building, go to Manage, and we'll choose a project location. And then for that, we'll just go ahead and put in here, what is our project address? We can put in Stanford University or 943005 or whatever you have in mind there. Looks like Stanford, California is a known place. Okay, we have some weather stations that are here close to the campus. We'll just go ahead and choose the default one. Say OK. And that'll be enough. That at least is a starting point. It's at least going to give us the right latitude and longitude and temperature profiles and all that good stuff. Okay, for right now, let's just go ahead and leave the building kind of oriented so that the north of the screen is also the north of the building and south of the screen, just for simplicity. We can change that later, but for right now, let's kind of leave it relatively simple. And what we want to do is actually to start putting down some walls and trying to make something that's a little bit interesting. So I'm going to draw a building shape. It's going to be a little bit more than a basic box, but it doesn't have to be much more than that. And we're just going to start with something that's going from level 1 to level 2. We may put a little more interesting roof on it, but let's just kind of put down some basic walls. We'll assign some properties to those walls, then start putting in windows and curtain walls and think about how all those things could work together. So to place the walls, if you haven't played around with Revit in the past, go ahead and we'll get you through this. Actually, we should probably do a special little tutorial session for people who are new and haven't played around with Revit in the past, just to get you going with it. But hopefully we'll get you through this today, and even after I kind of make my basic little box, I'll put it up on coursework, so if it's new to you, you won't have to worry about the modeling burden right up front. So I'm going to go to the Wall tool as a starting point, and just kind of choose a location for the walls. Now, when I choose the Wall tool, I have a couple big choices that we need to pay attention to. One is how high the wall is as we get going with modeling. By default, it's that unconnected 20, and I don't want it to be that. I'm going to just make it go up to level 2 for right now. So just going up to whatever height level 2 is. And I can think about the properties of the wall. And we can start by making them generic 8, or we could actually even start thinking ahead to what the thermal properties of the wall might be. So we got a lot of different wall constructions defined here. Yeah, we could use one of these as our wall type, and each of these different wall constructions not only have a thickness and materials, but it has some thermal properties that are associated with it. And let's try something that's let's just go with generic first, and I'll kind of switch from there. We'll change those at the same time. I'm just going to put in a generic 8-inch wall. And I can start drawing straight lines. I have these different line drawing tools. If you just want to draw a box, you can use that one, or you can draw lines that will connect together. I'm going to do some lines, and I'm going to make a basic, kind of like U-shaped building. So it's going to come up here, kind of come back across here. Maybe just have like a little U-shaped courtyard in here, something like that. But again, the precise shape isn't very important for what we're going to do today. So I have some idea of, this is going to be some sort of space. Maybe there's like a lobby here, and there's like a gallery on either side, or there's two different functions, but some sort of central space there. And that's enough to get us going. Okay. Along with this basic box, let's go ahead and I'm going to put it in 3D, just because I like to look at things that way instead. We need to put a floor and a ceiling or a roof on this space. So we can do that with the floor and the roof tools. And again, that's not going to be very tough for people who've did it last quarter. We'll just take the architectural floors. And again, choose some sort of floor there. We'll kind of worry about its materials in just a second. So I'll choose the generic floor. Then I can draw the boundary of that floor or pick the boundary of that floor. I tend to like to pick because the pick tool then locks the floor boundary to the wall boundary. And I'll even do that in the level 1 floor plan view. That might be a little bit easier. Let me zoom on in here. And then I will choose, of all these tools, there's drawing tools and picking tools. The picking tool is the one that looks like a little green arrow that's pointing at a wall. Let me kind of see if I can show you that without it kind of going away right there. So I'll choose that. Then I can pick, and I'm going to actually sort of pick just to the outside. Cover that over. And now I have some floor in there. Okay. Once we have a complete loop all the way around, we can hit the check mark to go ahead and close that. And when we do close that, we'll get a nice floor under there. Again, just a generic material for right now. Again, if this is a little confusing because you haven't played with the modeling tools yet, no worries. I'll upload this for you in just a second. And the final piece we're going to put on here really is a roof of some type. And roof is very similar to the floor. The roof typically we just have a little bit of overhang to it. Okay, I'll start with a flat roof and we'll make it sloped later. So let's just kind of start with a flat roof on this thing. So in the same sort of sense, I'm going to choose the roof tool. It's going to even ask me, because I'm in 3D view right now, it's going to ask me what level do you want to put it on, and I do want to put it up to the 2nd level. So I'm going to say yes to that. Then with the roof tool, there's really not too much we have to define differently. We'll let this be a generic 12-inch roof for right now. A couple things we do want to pay attention to, though, are the whole notion of, are the surfaces we're going to connect, or the boundaries we're going to connect, going to define a slope, because the roof is going to slope up from there. I'm going to turn that off so it's going to be flat. And also, I'm going to put a little overhang on the roof. We could have it right at 0. It would stop right at the wall edge, but I'm going to give it, even like a 1-foot overhang, just as a starting point. And we'll go from there. Typically, roofs do have an overhang of some type to protect the walls, unless they have a parapet on the outside to kind of keep the roof hidden. But we'll put a little overhang in there. So, and again, we'll talk about overhangs and what a good overhang is in a little bit. So I can choose the walls here. I can go to level 2 floor plan either way, but choose okay, and hopefully that looks like a complete boundary. And when you get all done, get a nice little flat roof on it. So again, a pretty boring building, but it's going to be a starting point for us. So I'll just go ahead and start it there. Okay, now let me save this one away so I can share it with you in case that's, you haven't had the experience with the modeling tools. I'm going to save this out, and I'm going to put it, just on my desktop for right now. I'll call this session 4 start. And then what I'll do is I'll put that up on coursework. Let me log in here. See if it likes me on this. Since I logged in the other day from the Mac side, it doesn't know about my PC side, so I have to kind of let it know about that. Put in a magic code. Oops. Which just changed right as I was about to... Hey, stop changing. It keeps on changing faster than I can type it. Oh, come on! Already been used. What do you mean it's already been used? You just gave it to me. Okay, back again. Let's try this one more time. Log it in. Hopefully you won't have as much problem logging in. Okay, we're back over here. Let's try that. Okay, that worked. So again, all I'm doing is I'm saving it up there. Don't worry if you have a building that looks good, you don't have to download this one. But if you, again, don't have a building and you want something to play along so you can follow with us, we'll go ahead and download this. And we'll just make a folder out here for session 4. And then within that, I'll just add that folder, or add that file. Where did I put it? I think I put it on my desktop. There it is. Hold the copyright. Looks good. Okay, so if you haven't played with Revit, please go out there to coursework. Try downloading that. At least get started with just see if you can bring that in. Just go ahead and try to go ahead and bring that in so we can sort of play along with this together in terms of the different materials. Okay, so for this little box, do most people have a building to play with? Okay, excellent. For this little box, let's take a look at the thermal properties and really how they change. So for example, on that roof, this generic 12-inch roof probably doesn't have very much of a thermal property at all right now. Generic just doesn't have a heat transfer coefficient, a thermal resistance, or a thermal mass right now. So if we choose a different type of roof assembly, we can start getting some of those things. So if I go popping around in here and look through some of the default ones, I have sort of wood rafters, I have steel trusses that have an insulated deck on them. Let's just kind of take a look and see what we kind of like in terms of different properties. And if these don't actually fit what we want, we want to put a green roof on there, we want to have some different sort of properties, we can duplicate these and create a new one that has its own set of properties to it. But if we went with, for example, with that wood rafter roof as a starting point, okay, it has a U value, that's how quickly things will flow through, of 0.01, a thermal resistance of 57.8. That's pretty good. That's pretty tight in the scheme of things. Not much is flowing through there per hour. It also has a thermal mass in terms of BTU per degree Fahrenheit of 1.41. Okay, let's kind of hold on to that number for a second in terms of what that really means. Let me go shifting over to, instead of that roof, actually I shouldn't have said okay. That was the wood roof, that was the wood rafter roof. Let's go to the other one, the steel truss. Nope, okay. So, in terms of this one actually has a thermal resistance of, interesting, 113. That is considered a very, very tight roof in terms of, there's very little heat flowing through that at all. Okay. Its thermal mass, though, is a little bit different. 2.08. It's higher. Okay. And we want to actually start to think about that a little bit. Let me try another roof that will really give me a good sense about really what the range of values I might expect to be in here are. Okay. For example, one material that I know has a really high, what I think of as a high thermal mass, it has a high thermal ability to collect and store and re-radiate, is concrete. So let me try this just to kind of calibrate my expectations. Let's say it was a concrete roof. Not necessarily a great choice structurally, or it could be, but let's just kind of see what that would be like. So if I change this instead to, I'm going to just say that's going to be, I duplicate it, a concrete 8-inch roof. Okay, just changing the name isn't enough. What I'm going to do is actually go through and knock out some of these layers of materials. So I'm going to knock out the finish layers and the insulation. I'm going to knock out that and really just come up with just an 8-inch layer of concrete. So I can choose the material concrete. See if I can find it here in my library. Say OK. Okay. It has a thermal mass of, well, look at heat transfer 0.9, thermal resistance 1.1. So not a great material at all in terms of resisting the heat flowing through it. Heat's going to flow right through that pretty readily because as opposed to 50 or 100, it only has a value of like 1 on the resistance side or looking at it the other way, as opposed to being 0.01 or 0.03, it's 0.9. So there's a lot more heat flowing through that material. However, it does have an interesting property. This thermal mass, its thermal mass is 15 as opposed to 1 or 2. So if that does go ahead and hit the sun hits it and it starts absorbing solar radiation, like it has a lot more mass for storing, like a battery, that and then re-radiating out slowly through the night when it might be doing some good. So this issue of the thermal mass as being the third kind of property to think about tends to come in sort of very, very handy sometimes, in that when we want to think about a building that will actually store and retain and kind of re-radiate heat slowly throughout space, we'll often use a material like concrete, or tile is another one. You know, stone-like materials have a really high thermal mass. Even tile on top of a mortar of a bed of concrete or a bed of mortar, that also has a really high thermal mass. So really, one of the requirements that's even in like the requirements for going through and building a house these days, the Title 24 requirements, you tend to have a certain amount of thermal mass in the house so that it will actually store and slowly re-radiate the heat, as opposed to just having it all flow back out very quickly through the walls. So those things kind of work together. Let's think about how we can actually get them to work together. Okay, but let's go ahead and choose some material for the roof. And I'm just going to, for right now, choose the steel truss. I'll go with one that has relatively low kind of thermal mass, but incredibly good thermal performance. That means that heat's not going to flow out through it, but it's not going to store heat for me very well either. Okay, that's kind of okay. Let's think about what we would like our wall surface to be. Our wall surface is currently kind of a generic 8-inch wall, again, that doesn't have any thermal properties. Now, just for our starting point building, you have any suggestions? Oh, it's kind of like a little museum-y exhibition space. What do you think might be a good wall surface? Yeah, no wrong choices. Yeah, it's just like, what could you imagine being on the side there? We'll just kind of take a look at the thermal properties and kind of work with them. So, what are we? We're kind of in Northern California at Stanford. Is this, is this an extreme weather climate or a relatively mild climate? Relatively mild in the scheme of things. If I just looked at the Title 24 requirements, they would want to have, either R13 or R19, something like that. If it was a house, they'd want R13 or R19, somewhere in there. It's not incredibly cold outside, but something like that. So, as you think about, if this were being built on campus, like what sort of wall surfaces and materials are built on the, on the buildings around campus here? Like, what do you sort of see on buildings right now? Short of the old quad. The old quad has its own kind of unique construction, but for some of the newer buildings being built on campus, what kind of walls do they typically have? Stucco. That's kind of a fairly standard sort of system around here. Some things are built out of wood and have shingles on them, but stucco is a really common surface. If I look just within these standard materials, the one that's probably closest to that of the exterior wall surfaces is what this EIFS. What EIFS is, it's almost like rigid foam that's covered with a layer of stucco. So if you ever go up to a building that's being built and it's covered with, it'll often be kind of this yellow foam material. It's like rigid foam board or something like that. It'll get stuccoed over. That's what it is. It's a system called EIFS. We could also put a wood wall up and cover it with stucco, but let's go with EIFS for now. That's kind of okay. In terms of the properties, let's take a look at it and see what we can say about that wall. So, what's we got here? Mineral resistance, 66. There ain't a whole lot of heat flowing through that. That's a pretty resistive wall. Thermal mass, 1.45. Okay, not very good at storing heat though either. Okay, so pretty much as long as we have the heat trapped in there, everything's good. But it doesn't really do a very good job of storing the heat. Another thing about this is that, if the sun is beating down on the outside of it, and we're trying to absorb the energy from the sun beating down the outside and getting it to re-radiate, this wouldn't be a very good wall, because it's not going to do a very good job of absorbing and storing it. Okay. If we went with a concrete wall, that'd be a much different sort of performance. Okay, let's take a look at the floor now. Floor again, kind of big generic surface right now. In terms of what's available for the floor, we have all these generic ones, wood joists and things like that. Lightweight concrete on metal deck. If this were actually going to be built outside and put on the ground, okay, somewhere around here, we'd probably want a different floor type. It'd actually just be like 6 inches of concrete, or it could be 8 inches, but probably 6 inches of concrete would be sufficient. Yeah, that's kind of what we call slab on grade, where we just put a concrete slab down. It's kind of a very inexpensive way of putting a floor down. Okay. And if we did something like that, I could take that generic floor and dupe it. And I'll just make it low concrete, 6 inches. And for the properties, give it like 6 inches. And again, assign it the material concrete. Now let's think about why concrete floors are a pretty good surface. Concrete has a 6-inch floor, you know, it does have this pretty good value of thermal mass. Okay, but on the other hand, thermal resistance is really pretty poor here. You know, only 0.8. That's not very good in the scheme of things. Okay. Why, if you're trying to go ahead and put thermal mass in the building, is the floor a good place to put it? And it kind of gets into what we talked about last time with the weather and how it applies. So, what is special about the floor and kind of being down on the ground?
The temperature is relatively inert.
Exactly, yeah. It's that constant temperature. So the cool thing about being down on the ground is, since it's not fluctuating, it's not going from 15 degrees to 100 degrees and down to 15 degrees. It's pretty much always at 60 degrees or something like that. The cool thing is, you know, not cool, the good attribute that it has to it is that the fact that it has really poor thermal resistance doesn't really bother us very much. It actually is okay since it has a relatively constant temperature. We don't have to worry about heat conducting through it very much. But it does have really good thermal mass. So how's that going to benefit us? That's going to be, if we have some sort of heating system in the building, it doesn't really matter what sun's energy, even if we have a heating system in the building and forced air or radiant heat is being used to heat the air in the building, that floor is going to constantly be absorbing that heat and then re-radiating it at times when we're not heating the building. So that floor is like this big old buffer that just kind of keeps on storing energy and re-radiating it and kind of keep things up. Which is why you might wonder if, as you wander around inside the Y2E2 building and you've seen all these polished concrete floors and you wonder why they're all concrete, it's not just strictly the idea that it was a cheap surface and it was a very inexpensive way to do it. Yeah, it actually has this really good thermal property to the whole thing. So, for the floor, going back to the Y2E2 building, what happens if you take that incredibly nice thermal mass, okay, and you put a whole lot of carpeting all over it? Okay. And carpeting, well, actually, let's even kind of think about that. Let's take this concrete floor and put a layer of carpeting on top of it. Let's put one on top. See if I can find carpeting. There's carpet. Say, okay, I'm going to put like 1 inch of concrete or carpet on or something like that. 1 foot. That'd be a little bit much. That'd be a thick rug. Interesting. It doesn't seem to change it too much. It has a slight effect on it. Carpeting has this funny sort of effect in the scheme of things that it's nice for us. We kind of like to walk on it and stuff like that. But when you put the carpeting on top of the concrete, like the heat can't necessarily, it's a good insulator. Carpeting is a good insulator. So the heat can't necessarily get to the concrete, so the concrete can absorb it and re-radiate it. So even in this building, when everyone moved in, there's a big old battle between the folks who liked the concrete floor and a lot of the folks who wanted to go put area rugs in and things to make it a little softer and cushier and a little homier, because in a weird sort of way, it was nice for their office to it sort of felt good underfoot, it kind of felt warm. It was almost defeating the purpose of the concrete floor to go ahead and put that carpeting in there. Okay, so watch out for that. I talk about this being concrete as a floor, but the same thing would sort of be true, if you had like a stone floor or a terrazzo floor, any of these materials that are these hard surfaces that, What's the disadvantage? Have you ever had, walked into a bathroom on a cold morning that has a stone floor? Like, what's the problem? You're shaking your head. So what's?
Very uncomfortable.
It's very uncomfortable. It's very cold. Yeah, and stuff like that. So the good and the bad of this whole strategy is if the house gets really cold, the floor is going to get really cold, and it takes quite a while to heat up. So even if the heat comes on in the morning, it takes a while for the floor to kind of catch up with you. On the other hand, if the heat's on throughout the day and you stop heating, the floor will kind of re-radiate that through. But some people do and don't like that in terms of a kind of a thermal performance. So just going to watch out for that. Okay, but we'll talk about later in mechanical systems how you can run hot water pipes through the floor, and that's actually kind of a nice toasty, that feels really good, to kind of have that warm floor and kind of be on top of it. Okay, but you're choosing these basic thermal properties. We'll leave it at that for now. And I'll just leave it as the concrete. I'm going to take that carpeting back off. Say goodbye to you. Okay, we got our basic thermal properties. We sort of have some notion about where we can store heat, what's not going to store heat so well. That's okay. Let's go put some windows in this place. This place needs a little way to get in and a little bit of light in there and stuff like that. So let's talk about that. There are, under the Architecture tab, the Window tool available. And windows, again, individually have U values to them. And we can go shopping for windows that have better U values. We can accept the standard values. But each of those different windows is going to basically let a little bit of heat radiate out of the surface. So if I went through, and I'll put some windows on this side wall over here. I'll put some big old windows in here. Just kind of placing them on the side here. Each and every one of those windows that I go placing on there has a couple of different effects. Let's think about what it does. Okay, from an energy standpoint, what's that window doing to me from an energy standpoint compared to a wall? Okay, so if I look at the thermal properties of that window and I say that that window has an R value of 1.5 as opposed to the wall around it which has an R value of, what was it, like 40 or 50 or something like that. What was the R value of this? Oh, that's still a generic wall. Let me change all the different walls so they have these properties. To change all the walls to be, what did I assign to the front one? Was it the EIFS walls? Yep. No, I guess I didn't change any of them. Oh, that one. I changed that one little wall. Okay. Well, I could either do this in the floor plan view and the level 3 view. If I go to the floor plan view, what I need to do is just basically, you can sort of see that wall's a little fatter now. I can choose all the walls, I can click, I can control click, I can control click. I can do that. The other way to do it that actually is a little bit quicker, if you have a whole chain of continuous walls going all the way, I just want to grab them all at once. Just hover over one, just hover. I'm not really kind of holding anything down, just pointing the mouse over it. Hit the tab key, and you'll chain. You'll get the whole bunch of them. Then I can click. You'll say there's multiple types selected because I was somewhere between. And I'll say EIFS or any of the wall types. That was just a quickie way to change them all at once. But now that I'm looking at this floor plan and I'm looking at my envelope, so here's my wall. My wall has this thermal property of, what, 66 as an R value. My window here has a thermal property of 1.5. So what is it? Somehow for every square inch of window, okay, we're losing about 40 times the heat, or about 40 times the heat is moving through every square inch of window compared to the wall right now. Good. Again, there's reasons for that. There's trade-offs and things we can do to that. Clearly, we might want to go thinking about sort of buying some higher performance window. 0.64 is actually pretty bad in the scheme of things. Right now, I think even for Title 24 in California, we have to get them to be around like 0.32 or 0.35 or something like that. So we could definitely go out for higher performance windows. Okay, and that would actually help. But no matter what we do, windows are always going to sort of radiate more than the other, than the walls. Okay, now windows, they're kind of cool in terms of the scheme that is going on though. Like, why are we putting the windows in? What is the advantage of the windows? Okay, besides the fact that we don't like living in a concrete box. Well, yeah, so they definitely have an aesthetic value in terms of what's going on. But really, what do windows buy us in terms of the interior experience from an energy standpoint? What do windows actually buy?
Daylighting.
Excellent, daylighting. So let's kind of think about how some of these things kind of work together. So daylighting, yeah, tends to be a good thing. If we don't have daylighting, what do we have to supply? Yeah, artificial lights. Okay, so I'll call them like, yeah, artificial lighting. And what's the energy impact of those two? Artificial lighting, we need a little bit of electricity. There's going to be so many watts of energy, whatever it is in there, you know, whether it's a 100-watt bulb or whatever it is. Okay, daylighting, like 0 watts. That's kind of good. Okay, but, okay, it even goes a little bit further than that because artificial lighting does sort of a very interesting thing. All that 100 watts, it doesn't just disappear. You know, it actually generates heat. Okay, so that 100 watts actually turns into heat. Okay, the way a lot of things turn into heat. People sort of forget about watts and how important they are, but you know, as we are standing here in the building, we are actually putting out a lot of heat. We're little furnaces. You know, all that kind of food and the energy we're burning and stuff like that, it turns into something and it turns into heat energy, and we actually radiate heat constantly. So if there's 40 of us in this room, we're actually radiating a fair amount of heat. Like all these computers and these screens, they're radiating a fair amount of heat. If you ever sit up here, come up here sometime and stand in front of one of these things. These actually radiate a fair amount of heat. It actually is pretty warm kind of right in front of these things. And this is all putting heat into the room. Okay, so all that heat is coming in, and is that a good thing or a bad thing? Ah, yes. Okay, so, yeah. When is it a good thing?
When this quarter, sir.
Exactly. So when we're in a heating cycle, when it's cold outside and we need to be adding heat, yeah, then it's a positive. Okay. However, when we're in a cooling cycle, okay, in the middle of summer at 4 in the afternoon, when like the heat's beating down on the building, you know, have you ever had people, they say just turn off the lights? It actually does make a difference. Okay, so you get to sort of think about these things, and these things sort of work, you know, together in that to the extent that we can use daylighting to supply our needs without introducing heat, that often has a double effect where we not only sort of reduce the direct consumption, but we also reduce the loading that's actually going to be on the heating and cooling system. Okay, so they all kind of work together. It's really weird in terms of what's driving buildings. You know, whether it's more of a heating problem or a cooling problem, or optimally you'll design a building that'll work well for both seasons. Okay, you really have to start to think about this whole notion of really what's going to work best at different times. So, I don't know, hold that thought, because we're going to kind of come back to that in just a second. So, we're hanging around over here. We put some basic light in our building. Let me zero out here. I'll put some more kind of maybe windows on the other side. Okay, I got some lights on the other side. We'll leave it at that for now. Okay, we're doing pretty good. We got this building. We sort of understand we got these windows here. We understand there's going to be a loss relative to those different windows over there, but hopefully it's going to introduce that daylighting to kind of make up for the effect of the heat that we're losing through them. Yeah, hopefully there's some good trade-off in that. Besides the fact that just generally, you know, we need windows in a place so that it's a, you know, nice place. No one likes to live in a concrete bunker, stuff like that. Okay, let us stop and pause there for just a second, and kind of think about how we could even start analyzing this a little bit. So we got some sort of starting point on our design here. It's not a really great building just yet, but we've got to give it a starting point. If we wanted to go through and analyze it, here's what we would do. We could go through and, like we've done in the past couple days, go through and add a room to it. Okay, the room tools on the architecture tab. So add a room to it. when we add a room to it, there's just a couple things we need to do. We need to make sure that the room does go all the way up to the roof so that there's no kind of gap at the top. So I'm going to say that it goes from 0 to 10. If I wanted to, I could even say it goes to 0 to 20 or 0 to 30. It really won't matter because rooms are smart enough that though, as soon as they hit the floor or the roof above, they'll cut off. It sort of knows that. Okay. We'll also go ahead and within the room and area, turn on something that's important over here called area and volume calculations. We can kind of turn that on, area and volumes. Okay. And now, if we wanted to, we could export this GBXML file, take it over Ecotect and stuff like that. So if we really want to understand the hard science behind it, we can take it to Ecotect and look at it that way. If we just want a really quick answer to what the energy performance of the building is now, we can send it over to the cloud service, and we don't even have to take it to Ecotect. But as a starting point, let's go ahead and take it over to Ecotect just so you can sort of see this and understand the science behind it. I will go through and I will say, let me go through and export some GBXML. This is the basic shape we are working with right now. That's kind of the simple surfaces that are going to represent this. It's an office sort of space in Stanford, California. If I turn on the include thermal properties, that'll go through and then for all the wall assemblies that I've been assigning and their R values and their thermal mass properties, it'll carry that information too, which tends to be a good thing. Okay. The other thing we need to worry about is the notion of what is this building? And this is actually sort of related to the internal loads. This is more kind of a thermal consideration than a daylighting consideration. So let's talk about the differences here. What's the difference in terms of the heat generated between, for example, an office, a convention center, a penitentiary, or even a religious building? They're all kind of interesting different buildings. They have different sort of profiles to them. So offices, what can you tell me about an office? If I tell you it's an office space, what can you sort of assume relative to the people and the hours and how this building is going to get used? So for an office space, there is a density, a common density of really, oh, if I'm going to take up 25 square feet, I can take with the total number of square feet in the building. I can assume how many people and how much equipment they're going to have. I can also probably assume something about their working patterns. You know, they're kind of 8 to 5-ish. They're generating heat then. I need to keep the heat on sort of from 8 to 5. I probably don't need to keep the heat on from 2 in the morning to 6 in the morning. Okay. On the other hand, if I go ahead and look at a school, schools are a little bit different, you know. So you probably know, relative to the way this building gets used, that we're not kind of 8 to 5 people. Okay, we may have more people in there. Other ones that are sort of interesting are, convention center. How do convention centers work? If the convention centers tend to have more people or less people than like an office? It tends to be more. We tend to be kind of packed in there much more densely, although not all the time. You know, when it's in use, it's going to be packed in there. Yeah. The other one that's kind of interesting is, and this is kind of a funny one, that way you think about why it's so different, religious buildings. You know, what happens with religious buildings? They're these big auditoriums with hundreds of people sitting in them for 3 hours on Sunday morning, or Saturday night, or whatever it is, or Friday night, whatever it is, it sort of seems to make sense. So they have a very different kind of profile for them. So the profile actually does make a difference. It won't matter for daylighting, but it does matter from an energy standpoint. So that's what that choice is all about. Based on what you choose there, performing arts theaters, again, we're going to pack you in there really, really tight, but only on Friday and Saturday night. It's one of those sort of things. I'll just leave it as, we'll just leave it as a museum. That's kind of what I sort of said it was going to be in here. Say OK. Let me save this away out to my desktop.